Have you ever stopped to think about what a diamond, the air you're breathing right now, and a distant star all have in common? It sounds like a riddle, right? Well, they all follow the same secret set of rules. And today we're going to pull back the curtain on that hidden rulebook of matter. So let's just start with a puzzle. What on earth does a solid, cold block of ice have in common with the invisible air all around you? I mean, one is hard, you can hold it, the other you can't even see. But believe it or not, deep down, they're playing by the exact same set of rules. And the name of that rulebook? It's the particle theory of matter. It's this one beautiful idea that everything, and I mean everything, is made of these impossibly tiny particles that are constantly moving. This isn't just some abstract concept. It's literally the operating system for our entire physical world. So what is this universal code that everything has to follow? Well, it's actually surprisingly simple. It all boils down to just 5 core principles. Think of them as the unbreakable laws that every single particle in the universe has to obey, no exceptions.
Okay, these 5 rules are the foundation. Rule number 1, everything is made of tiny particles. Simple enough. Rule 2, if you have a pure substance, like pure water, all of its particles are identical copies of each other. Rule 3, and this one's a bit of a mind bender, these particles are always moving. They never, ever stop. They're always jiggling or zipping around. Fourth, there are always little gaps of empty space between these particles. That's right, nothing is truly solid. And finally, rule number 5, the particles are attracted to each other. There's this invisible pull, like a glue trying to hold them together. If you can get your head around these 5 rules, you've basically got the master key to understanding matter.
All right, so with those 5 rules in our back pocket, we can now look at the world around us and actually understand it. We can see how these rules explain the 3 states of matter we deal with every single day: solids, liquids, and gases. This is where the theory really comes to life. Let's start with a solid. Think of a brick or a diamond. In a solid, that attraction force we talked about, it's super strong. It's so strong that it locks all the particles into a neat, tight grid. Now remember, they're still moving, they can't stop, but they're locked in place, so all they can do is just vibrate, kind of jiggle on the spot. And that is exactly why a solid holds its own shape. Now let's look at liquids and gases. In a liquid, like water, those attraction forces are a bit weaker. The particles are still pretty close, but now they have enough freedom to slide right past each other, and that's what makes a liquid flow and take the shape of whatever you pour it into. But in a gas, man, the attraction has basically given up. The particles have so much energy that they just zip around like crazy, flying off in all directions to completely fill any container you put them in. It really is a battle between that sticky attraction and the freedom of motion. So we've got this constant tug of war between attraction and motion. But what if we could throw a wild card into the mix? Something that could tip the scales one way or the other? Well, we can. And that game changer is heat. So here's how it works, and it's actually really simple. Heat is just energy. When you add heat to something, you're giving its particles more energy. We call this energy of motion kinetic energy. So the more kinetic energy a particle gets, the faster and more violently it moves. It's a direct, simple relationship. You add heat, particles speed up. That's it.
And that simple fact, more heat means more speed, explains why things expand and contract. When you heat something up, its particles start moving faster. They bump into each other harder, and they push each other further apart. The whole substance expands. And the opposite is true too. When you cool something down, you're taking energy away. The particles slow down, and those attractive forces can pull them back in closer together. The substance contracts. See? It all makes sense.
Okay, this is where it all clicks together. We've talked about the states of matter, and we've talked about heat. Now we can see how by adding or taking away heat, we can literally force a substance to change from a solid to a liquid to a gas. This is how you get from a block of ice to a puddle of water, and from that puddle to a cloud of steam.
Let's just follow the journey. You take a solid and add heat. That's melting. The particles start vibrating so fiercely that they break out of their rigid positions and start sliding around as a liquid. Okay, now add even more heat to that liquid. That's evaporation. The particles get so much energy they completely overcome the attraction and escape, flying off as a gas. Now let's go backward. Take that gas and cool it down. Condensation. The particles slow down enough that their attraction can grab them again, pulling them back into a liquid. And if you cool that liquid down even more, you get freezing. The particles slow down so much they just lock right back into that solid, organized pattern.
All right, so you've heard the rules, you've seen how it all works. Let's put this theory to the test. Time for a quick pop quiz. You ready? First question, why does a solid ice cube just sit there? Why does it keep its cube shape all on its own? Think back to those rules about solids.
You got it. It's because those attractive forces are so incredibly strong, they lock all the little water particles into a fixed, rigid grid. They're still vibrating in place, but they can't go anywhere, so the cube holds its shape. Perfect.
Okay, next up. When you boil a pot of water, why does the steam that comes puffing out take up so much more room than the liquid water it came from?
It's all about that empty space. When water turns into steam, the particles get a massive boost of energy from the heat. They completely break free of those attractive forces and just fly far, far apart from each other. Most of what we call steam is actually just the huge empty gaps between those fast-moving particles.
So you see, the particle theory isn't just a bunch of facts to memorize. It's a powerful tool. It's like having the key that unlocks why everything in the physical world behaves the way it does, from a melting ice cube to an exploding star.
And that leaves us with one final kind of mind-blowing thought. If everything, this desk, the air, you, is all just tiny particles with a whole lot of empty space in between, what does it actually mean to touch something? You're not really touching a solid object. So what is that feeling? Something to chew on. Thanks for digging into this with me.